So it's my great pleasure to introduce Connell Elliott, who's going to talk about automatic differentiation and a wonderful paper which I took great pleasure reading. So great that it received a distinguished paper award, which I have right here in my hand. Connell.
Thank you very much. Great, thank you. Put next there. All right, glad to be here. I think the slide will come up momentarily. Is that right? Screens are not on yet. Waiting for the screen to come on. There we go. What's happening? Oh, I forgot to plug in, did I? Thank you very much. Tested beforehand to make sure it would work, but it managed to plug it back in, it turns out. All right, thank you. Much better. Okay. So machine learning has been having a renaissance over the last few years, and they're pretty impressive results, which I think have affected quite a few of us. At the heart of much of its success is something called automatic differentiation, which is the mechanized computation of derivatives in the calculus sense of functions that are expressed in programs. Okay? However, the AD algorithm, automatic differentiation algorithm, that's popularly used in machine learning, which is called backprop or backpropagation, is complicated and stateful. Okay? Why does it matter? Well, the complexity of the algorithm makes it difficult to understand, which makes it difficult to improve. And the statefulness, in particular, makes it non-trivial to parallelize. And these days, most performance comes from parallelism, particularly if you get massive parallelism. Okay, so this is one problem. The second problem is that programming systems for machine learning, and in particular for deep learning, are rather complex, and they present a model of graphs in which one writes programs that explicitly construct graphs that represent differentiable functions, even though we have a perfectly good way to express functions, namely our programming languages themselves, right? And in particular, functional programming languages. So in this talk today, I'm going to suggest a couple of solutions to these problems. First, a small collection of AD algorithms that are quite simple in great contrast to the literature and to popular use. These algorithms are calculated from very simple specifications. I think you'll find quite natural. They also seem to be very efficient in time and space. Don't have measurements to back that up. That's my personal impression. They're intrinsically parallel friendly, in part because they're purely functional. They're not imperative at all. And then secondly, the API, rather than a complex graph API, the programming interface is simply differentiation itself. As I said, we already have ways to talk about computable functions. Timer doesn't seem to be ticking. Should it be ticking down? Okay. So the work I'm talking about, great, is built on top of a paper I presented last year at ICFP called Compiling the Categories. The idea there was simply that you take regular functional code, happening written in Haskell, convert it to a particular vocabulary called category theory or categorical combinators, and then reinterpret that vocabulary in a variety of different ways. Those ways in the particular embodiment that I showed last year and we'll be using this year are simple type classes. So simple type class definitions are rather instances of type classes. So what is differentiation? Okay, that's the most important question. So differentiation is an operation on functions. So it takes a function from A to B, and it gives you another function from A to derivatives. Okay, so what are derivatives? Well, in general, derivatives are linear maps from A to B. So you might have been taught, as I was, that a derivative is something like a number, a vector, or a matrix, but really these are all different representations of the same notion, which is linear transformations. Okay, so if we want to understand how to compute derivatives on functions, it helps to look at the basic building blocks of functions themselves. Okay, so one is composition, sequential composition. If we know how to compose two functions, then the chain rule tells us how to differentiate their composition. And it says the derivative of a composition is the composition of derivatives. You probably learned it was the product of derivatives, but that product represents composition. Okay? Now there's another way to compose functions, which is in parallel. So I'm going to use this operation called fork. It takes two functions and kind of zips them together, these two functions that have the same domain, into one. And there's another lovely rule. It says the derivative of the fork of two functions is the fork of the derivatives of the two functions. Okay? And now there's just one more general rule, and it's the following. Every linear function is its own derivative. Okay? So for instance, the derivative of the identity function at any point in its domain is the identity function. You may have been taught it's something like 1 or the identity matrix, but again, those are just representations of linear maps. Okay? Now let's go back to the chain rule. There's one little wrinkle, which is the chain rule. I said it says that the derivative of G composed F is the derivative of G composed of derivative of F. But really we have to say where to sample them. And we have to sample G at F of A. So this means that the differentiation itself is not sort of directly simply compositional, because it needs to know not just the derivatives, but it needs to know F itself. So to make for a compositional algorithm, what do? We just enhance the specification. So in addition to computing the derivative with D, what we're going to do with D hat is carry along F itself. So we're going to carry along F and its derivative. That just means that, oops, did I hit the wrong button there? There we go. That just means that we're going to not throw away the original function. We're going to carry it along in parallel. Okay. Now the vocabulary that I just mentioned, identity, composition, first and second projections, and fork, this is not just a random collection of functions. This is the language of Cartesian categories. And so it's defined on functions, but it's defined on a lot of other function-like things, including linear maps, but other things as well. Okay? So now, there we go. What do? I've really kind of told you everything you need to know. You could finish this talk for me at this point if you had a little more time to prepare for it. But I'm going to show you how the pieces come together quite nicely. So as I said, we're going to represent differentiable functions by a function that, so really what we're doing is we're just going to build the answer into the representation. So how do we compute derivatives? We just represent functions with their derivatives. And so I'm just wrapping up in this new type wrapper D, a function from A to a regular value and its derivative. Okay, and the specification D hat, it just throws this new type wrapper around. Now, so that's what this kind of augmented differentiation is. Now, here's the specification of automatic differentiation. We say that D hat is a homomorphism over the vocabulary we're going to use. In other words, D hat preserves the structure of this vocabulary or distributes over the structure. And all I mean is exactly these 5 equations. So D hat of the identity is the identity. D hat of G composed F is D hat G composed D hat F, and so on. Okay? These 5 equations are algebra problems, and there's only one unknown per equation, and it's the operation on the right-hand side. Everything else is defined. So all we have to do is solve these 5 equations, and they're really independent, so solve them independently. And out pops this code. Okay? This is very easy to solve because I already told you by giving you those laws of differentiation of compose, sequential, parallel, and linear functions. Well, this is a perfectly good automatic differentiation algorithm, okay? But there's something very intriguing about it, which is if you look at this code and examine it a bit, or if you just examine the rules I showed you first, we can see that for each operation on differentiable functions, all I need out of linear maps, that is derivatives, is those same operations, okay? So this is a kind of a lovely formulation, but it also has a profound implication, which is that we can do automatic differentiation in a much more general setting, where instead of linear maps for this notion of derivatives, we can use any Cartesian category, that is, any notion that has this same vocabulary and that satisfies just the basic fundamental laws. Okay. And if we do this generalization, I'm going to move from one slide to the next. There we go. So all I've done from this slide to this slide is abstracted out the choice of linear maps. I made it into a parameter. That's that little subscript wiggly arrow. Okay. Otherwise, the code is the same. Also, I had to make the functionality I needed from that squiggly arrow explicit. Okay. So now we have generalized automatic differentiation. Well, there's a little wrinkle here. Negate and addition, if you look at the bottom, those operations are linear, so we can use the general linear rule. But multiplication is not linear. Multiplication is what's called bilinear. Okay. So let's look again at the definition of multiplication, the differentiable version, which I went through pretty fast before. Okay. We see, well, I've used a lambda expression here, and lambda expressions aren't interpretable in all these different settings directly. However, we can introduce a little bit more vocabulary, and this is all the new vocabulary we'll need. One is an operation for creating scalar linear transformations, and that's just a partial application of multiplication. And the other is an operation that I'm calling join, that's a dual to fork. And where fork took 2 functions, zipped them together and generated a pair, join will take 2 functions, put them together, and consume a pair. Okay? And it just uses addition as below. And now at the bottom of the slide, you can see we can redefine or re-express multiplication. using this new generalizable vocabulary. Okay. So now we take generalized automatic differentiation, and I want to specialize it for the first time, but I'll do it a few more times, to just linear maps represented as functions that happen to be linear, okay, that have the property of linearity. And it's a quite simple definition. It's almost entirely what you've seen before, just packaged up. Okay. However, there's a performance problem. So this certainly works. But usually when we do automatic differentiation, we're going to, at the very end, extract some kind of data representation, which could be a vector, like a gradient vector, or some kind of matrix. And the complexity of that operation, the cost of that operation, of extracting one of these data representations from a function representation of linear maps, is quadratic in the dimension of the domain. And for optimization, including machine learning, it's not uncommon for the domain to be like in the millions of dimensions. So that's a very bad number to be quadratic in. So that's why we would really want to use this representation for doing a high-dimensional optimization. So what we can do instead is not have to extract at the end by using a data representation all the way through. And this is what everybody really does. That data representation is usually matrices. Okay, so we can define a category of matrices. Now we have to figure out what the methods are. We just set up 5 algebra problems again, solve them, and out pops linear algebra. Okay, out pops matrix algebra, let's say. Okay, now there's another problem. Okay, well, an opportunity. If you look at matrix multiplication, it's associative. It has to be associative because it implements function composition, which is associative. Okay, but unlike function composition, it really matters a lot which way you orient, which way you associate. And so there are 2 extreme examples. One's called forward mode, where you associate all to the right. Reverse mode, where you associate all to the left. Reverse mode is much, much more efficient for gradient-based optimization, for these high-dimensional optimizations as used in machine learning. Okay? So what do? Fortunately, there's a nice little trick. It's been around for decades that allows us to reassociate composition to the left, and it's called continuation passing transformation. So we can take the idea of CPS, embed it into a little category, which I've defined here. Now we define a function, a cont, lowercase cont, that describes the relationship between, say, linear maps, for instance, and the CPS version. It's very simple. And again, we have 5 algebra problems. We solve them. We get, this code. Okay? It's quite simple. This is a correct implementation of reverse mode automatic differentiation. I think this is by far simpler than anything I've seen in the literature. And it's calculated. It's correct by construction. Now, here is what I call reverse mode AD without tears, and I call it that because I always want to cry when I read a paper on reverse mode AD in the literature. 6, thank you. Okay, good. This one says 1, that says 6. That one's right? Good, then I'm much relieved, thanks. All right, so here's the complete algorithm. This is the code. This is the complete implementation. Reverse mode AD is simply the simple generalized AD algorithm, specialized to, or instantiated with a representation of linear maps that is simply matrices, but the CPS version. So you take the CPS version of matrices, plug that into the general AD algorithm, and you get reverse mode AD, correct by construction. Okay, there's one more trick, and that's it. And the trick is a deep property of linear algebra. I don't know how long this has been known, probably more than 100 years. And it's the following. If we have a linear map from one vector space to another, so linear maps are defined over vector spaces. So if you have a linear map from one vector space to another, and that other is the scalar field for the vector space itself. In other words, if we have a linear map from a vector space to its own scalar field, then it's isomorphic to the vector space itself. Okay? So in this special case, you can represent linear maps simply as vectors themselves. This shows up in matrix form as a single row matrix. Okay, that's what it looks like. And so, of course, you can see it's isomorphic to the vector itself. Now, here's the trick. Linear maps from A to B, we can represent first in CPS form by a function from a B consumer to an A consumer. Okay, and these are linear consumers. But in the case of gradient-based optimization, the consumer is going to generate something in the scalar field itself. Why? It's because we're optimizing objective functions, and objective functions are functions to scalars. Okay? So we can represent a linear map from A to B in CPS form specifically to generate something in the scalar field. But then we can represent B linear S and A linear S simply as B and A itself. So the CPS form in this special case is isomorphic to just functions from B to A. Okay. Now, why is this so much better? Well, remember I said, when we had functions from A to B as a representation, it's very simple, it's certainly correct. But data extraction is quadratic in the dimension of A, which is large. When we're able to flip the function around, now data extraction is, the expense is quadratic in the dimension of B, which is 1. That's a great number to be quadratic in. Okay? So this, I believe, is the heart of backprop. Okay? And what does it look like? Well, to realize this idea, this duality idea, again, just to find a simple category called dual. This is a general construction. It has nothing to do with automatic differentiation or linear maps, just like the CPS transform was. Define this function as dual that relates the continuation category to the dual category. It's very simple. It just uses the isomorphism. That's what the dot and dot inverse are. And again, we form the 5 algebra problems, which are homomorphisms, always the same. And we solve those 5 algebra problems, and we get this code. And to me, this code is beautiful because it says, if you look at it, you see it says identity is identity. Composition is flipped composition. What I call in new 2 here is just this little utility that strips off new type wrappers, applies some operation, and rewraps them. Okay? So composition gets reversed. Projections at the x's. Projections become injections. Injections become projections. And fork and join trade places. And scaling, interestingly, is unchanged. Okay? Now, if you think about matrices, all I've done here is perform the transpose. So when you do matrix transposition, it's really doing dual vectors, or it's doing this dual transformation on the linear maps. All right, so now we have backpropagation, okay? So backpropagation this is the code. This is the implementation. It's the simple, generalized automatic differentiation, specialized to the dualized version of functions, okay? So remember I said we started with functions, terribly naive choice, horrible performance. We went to matrices, still some problems. We went to CPS, fixed some of the problems, but it's still a little complicated and involved matrices. But the really efficient one is just back all the way to the original naive choice, except dualized, and that's it. Okay. In conclusion, I've shown you some simple AD algorithms, mode independent, specializing to forward and reverse mode, but also all kinds of mixtures. Unlike the algorithms in literature, they're very simple. No graphs, no tapes, perturbation tags, partial derivatives, or mutations, certainly not mutation. They're intrinsically parallel friendly, and they're calculated from very simple, compelling specifications, from solving algebra problems that are given by these specifications. They generalize to all kinds of representations of derivatives, as well as things that aren't linear maps at all. Okay? And then they're easy to use because you can simply write Haskell code and differentiate. If you read the paper, which I hope you will, I give a bunch of examples. I have pictures, proofs. The proofs are in the extended version of the talk. And an example of the same algorithm, but to something that's not simply automatic differentiation, is automatic incremental computation. Okay.
Thanks, Carl. I thought this stuff looked pretty general already, but people are asking questions about possible further generalization. So Jeremy asks, your model depends on addition. Can the structure be made more general, not depending on numbers?
Yeah. Okay. So yeah, almost certainly. I think it can at least be applied to semirings. I don't know exactly what it needs. It could be simply a monoid. It might need to be commutative. So I think the answer is certainly yes. I'm not sure exactly where the line is.
Yeah. Okay, the basic building block identifies a space with its tangent space, and this assumption doesn't generalize to more sophisticated situations. Is this a limitation?
It might be, yeah. So there is a more general notion, a setting of calculus on manifolds, and it is a little more general than what the space here I described in terms of vector spaces. So I don't know the answer to that question.
Okay. So an question whenever it comes to machine learning? How does this support? Is there special stuff in there to support offloading to GPU?
Okay, so is there something special in here to support offloading GPU? I love this question because part of what's so delightful for me about solving this problem in the context of compiling the categories in more general setting is that you can write Haskell code, interpret it in the category of differentiable functions, unwrap the representation, which is simply another Haskell function, and reinterpret it in a different category. One of those categories is GPU accelerated functions, or better yet, FPGA accelerated functions, which is really where this work started. So yes, absolutely, but it doesn't need to be here, which is even better.
Okay, so more performance questions. Matt D asks, regarding matrix extraction performance, certain optimization algorithms only need the matrix vector product for a given vector instead of the entire matrix. Is there a high performance solution you'd recommend?
Let's see, would you repeat that part? They need matrix vector instead of what?
Only need a matrix vector product for a given vector instead of the entire matrix.
Yeah. So I didn't have time to talk about it, but if you read the paper, you'll find out that there are actually no matrix operations at all in this algorithm. So particularly in the backprop algorithm. They all go away. They're sort of in the derivation, but they get optimized away entirely.
Okay. Well, one more. Have you investigated the relation between the structure captured by your lollipop morphisms and additive categories?
And additive categories, yes, yeah, and that's in the paper as well. Yes, it really applies to a much more general setting.
Yeah. Okay. Thank you very much.
Thank you.